So in the last video, we took a look at being able to find the derivative using the very definition of the derivative, the limit definition. And what we found was that it was algebraically fairly rigorous to do that. There are a number of shortcut rules and techniques of being able to find derivatives. All right, so what we're going to do in this section is we're just going to take a brief overview. And this is one of the most important sections in the course, the techniques of differentiation. And what this tells us is that we're able to find the derivative very easily. All right, so just a few really basic rules is that one, if you took the derivative, so let's say we have our function, and that's going to lead us to the derivative of that function. All right, so let's say we just had a function that's a constant function. All right, the derivative of any constant is 0. Right, so this is like a table almost. So anytime you have a constant function and you want to find the derivative of that constant function, the derivative is 0. If you ever have an x, the derivative of x is 1. If you ever have cx, the derivative of cx is c. And remember in one of the problems that we looked at earlier, remember we had this function f at x was equal to negative 6x plus 3. That was in the first video in chapter 3. And then remember we found that the derivative was negative 6. So in this case right here, c would have been negative 6 for us. All right, so just illustrating that, kind of tying in what we had earlier to be able to show what the derivative is. All right. Another rule is that any derivative of an exponent, so if we have cx squared, or yeah, let's just say x to the nth power, all right, as long as n is a real number, then this is going to be equal to c times n times x to the n minus 1. So basically what you do is you just multiply c and n together and then you subtract 1. All right, that works really nicely because that makes things a lot easier. If you have the derivative of two functions, so let's say we have f plus g or even minus g. To find the derivative of two functions that are added and subtracted, you just find the derivative of each. So that would be f prime plus or minus g prime. If you have a constant times a function, the derivative of that will be a constant times the derivative of a function. Right? And the reason for that is because, remember, with the limit laws, and remember, a derivative is just a limit. All right? Remember, we could factor out a constant, or we could take the limit of two terms individually. All right, and that's where all this is coming from. So just kind of reminding you, for those of you that are really hardcore into the math, why is this true? It's because it's limit based. All right, so we can do all of this because a derivative is really just a limit when it comes down to it. All right, just a few more. Let's say we have a function of e to the x. The derivative of e to the x is e to the x. Okay, it's one of the only functions, there's very few of them, that the derivative ends up being itself. Natural log of x, the derivative of natural log x is 1 over x. Okay, remember, these are all slopes at any point on the function. Now, some notations of derivatives, because there are a lot of different notations for derivatives. So I just want to make sure that everybody understands that when they see the derivatives, what they really mean. So these are just notations. F prime at x is one that we've seen a lot. All right, so this is one notation of the derivative. dy dx, all right, that's the change in y and the change of divided by the change in x. All right, for those of you that are engineers and physicists, you might see delta y over delta x. That's another notation. All right. Most of the time in physics, you use delta as opposed to dy dx. Sometimes there's this differential operator, d, all right? So you might see like d of a function or something like that. Another one you might see is d dx, all right? So that's the derivative of some function with respect to x, all right? So these all mean the same thing. I just want to make sure that for those of you, when you work through my math lab, or if you're in physics or in another class, These are all different notations that you might see. All right, so how do we apply these rules? All right, so it's actually really easy. So we're going to take a look at a number of basic sorts of derivative operations. So really easy. We have our function, negative 10x to the 6th, that we want to find the derivative. So what we do is we just go back up, and it looks like it matches this rule to where we have cx to the nth power. And all we're going to do is we're just going to subtract 1 from the exponent and multiply by the exponent. So this is going to be equal to negative 10 times 6, which is the exponent, times x to the 6 minus 1, all right? Or negative 60x to the 5th. Right? And that would be the slope of that function at any point on that curve. All right, so remember, the derivative really represents the slope. So this is what we call f prime at x, okay? Or dy dx or ddx, whatever you want to call it. Another very simplistic example, 8 roots of t. Now you might go up here and you might think to yourself, okay, well, there's no examples of this at all right? There's no square root. That's because the power is hidden. Right? One of the things you might remember from pre-calculus is that you can rewrite this function to the 1/2 power. Okay, so remember working with your radical functions is that a square root is really disguised as a 1/2 power. And so now what we can do is we can use that cx to the n is c times n times x to the n minus 1. Right? So our derivative g prime at t is going to be equal to 8 times 1/2 times t to the 1/2 minus 1. And of course, we can simplify this, right? So be careful with this one because we do have to simplify it. Now, 8 times 1/2 is 4. And then we have t to the minus 1/2. So 1/2 minus 1 is minus 1/2. Another way to write this, remember your negative exponent rules, you can put the t in the denominator. So this is t to the 1/2 power. And then finally, remember 1/2 power is square root, right? So that means that we have 4 over the square root of t, all right? And that would be the derivative, which again is a slope. Before we end this video, I just want to make sure that we understand that the domain of the original function, all right? So, and this is just, I know the problem only asked you to be able to find the derivative, but just kind of a little bit more in depth for those of you that care. The derivative, or the domain, excuse me, of the original function is from 0 to infinity, right? Because that's where it's continuous, right? The original function is, you can plug in any value that's 0 or greater. But look at the derivative. The derivative's domain is not 0 to infinity, okay, inclusive. So we like to use this idea of differentiable. And differentiable basically means where does the function's derivative exist? And clearly for this one, it's exclusive 0 to infinity because we can't divide by 0. So what we can say is that the domain of f is from 0 inclusive to infinity, but f is differentiable over the open interval from 0 to infinity. All right, so keep that in mind, that just because a function has a derivative, or maybe the function exists at a specific point, it doesn't always mean it's a differentiable at that point. All right, 8 over root t, by the way, looks something like this, right? That's what the function would look like. All right, so right here at this point, at 0, 0, it is not differentiable, which means we can't find an equation of a tangent line, which means we can't use a local linear approximation, which means it doesn't have a slope at that point. All right, and that's just because the function's beginning there. We could approximate the slope by using some really small numbers like 0.001 or 0.0001, etc., but that would just make the function blow up. All right, so hopefully this gives you a basic overview as to some of the techniques for finding derivatives without using the definition. And in the next videos, what we're going to do is we're just going to do a few more of these techniques.